Hello, everyone. Welcome to the first video lecture on Bayesian deep learning. This one's about the motivation and model definition. We have high hopes for our current artificial intelligence systems. We hope that they can do things like drive our cars for us and also take care of us when we're sick. But in order to do these consequential tasks safely, we need them to have an internal model of uncertainty quantification. Consider, for instance, this picture on the left of driving at dusk. We want our models to have an uncertainty map that looks something like this, right? Where dark blue represents certainty and the lighter colors and reds represent uncertainty. We can see in this picture in particular, the uncertain regions are kind of up ahead beyond the car in front of us, but also areas like the bumper of the car in front of us. And naturally, when kind of bizarre events happen or anomalies, we want this uncertainty to inflate. And so here is a similar picture, but now there's kind of this blinding white light, and appropriately, the uncertainty map should recognize it and signal to the self-driving car that it should slow down. The problem is that our current neural networks are not too good at quantifying uncertainty. So consider just a simple neural network to make things more concrete. And say it's trained on MNIST, the well-known data set of handwritten digits. We can examine what happens to the softmax output probabilities for each class, 0 through 9. When we take this particular 3 as input and we slowly rotate it, we see that for the unrotated 3, the model is predicting it's a class 3 with near 100% probability. And we can begin to rotate the 3 a little bit to the left, and we see the model stays fairly robust and predicts 3 still above 90% confidence. But if we just rotate the 3 slightly more, almost imperceptibly from this image to this image, we see the class prediction changes from a 3 now to a 7 with over 80% confidence. And if we continue to rotate the image, things just go completely haywire, and it starts recommending kind of 4s with 100% confidence. If this model indeed were to have a notion of uncertainty, it should start to detect that the data is changing outside of the domain that it was trained on. And ideally, all of these probabilities for the classes would go down to 1 over 10, or the region of maximum uncertainty. Now, the model would be totally ambivalent between classes. And we can also think of this notion of uncertainty in a regression example. So here's a simple 1D regression problem where we have X as our features as our input and Y as our target or response. And say we have a true function in blue that we can observe, and we just observe the black dots. These are our observations. And I fit a two hidden layer 30 unit neural network to this data, and I got something like this, what's shown in the red line. And yeah, it looks like a fairly good fit. It's doing fairly sensible things in the regions it hasn't seen data by interpolating here, extrapolating here. But of course, this is just one particular fit. And neural networks have many degrees of freedom that they could fit this data many different ways. So, one could imagine I fit this model again, and it does something slightly different. Maybe it goes here, and then here, and here, and then here. That'll still be a fairly reasonable fit. And I've done just that. And so here's 5 neural networks fit to the same data set, just each with a different random seed. And we see, accordingly, they all fit the data pretty well in these regions. They all do different things in these regions where we haven't seen data. These are the regions where kind of we want uncertainty to be well quantified. So Bayesian neural networks are one way to think about and possibly solve this problem. And so the core idea of how they do that is where a traditional network just is fit with one point estimate, right? For each weight value has one particular value associated with it. Bayesian neural network is kind of like a self ensemble all at once, in that instead of just a particular weight value, we have a distribution over weights. And these distribution will reflect these uncertainties that I've been talking about. And how we kind of quantify this uncertainty and bring it to bear in practice is through something called a predictive distribution, where we take this distribution on the weights, PW, given some data here, and for a new data point, x star, we will define the predictive distribution by integrating over this distribution on the weights. This gives us this distribution here, and we can visualize it like so for that same regression problem. Now we see all those different fits that we were just showing kind of point estimates for before have been kind of elegantly unified into one model, where the dark green line is the mean of the predictive distribution, and the green shaded regions are 2 standard deviations from the mean. And so now let's look into the details of how we define a Bayesian neural network. So our data model, or our observation model, would just be P of y given x and all of the weights for L layers. And unless I state otherwise, we'll assume the neural networks are fully connected and feed forward. And so for a problem like real valued regression, we'll assume this conditional distribution here is normal with a mean determined by the neural network and some response noise sigma squared naught. Or for classification, we'll assume this conditional distribution is a categorical one, where the probabilities are given by the neural network with an appropriate transformation function like a softmax output. And so given this is our observation model, to make it Bayesian, we of course have to define some prior on the parameters. And so, of course, these are our parameters, use the weight. So we'll have to define priors, P, W1, P, WL. And so how might we do that? Well, the first you get to do the simplest thing is just say we have a prior per weight. Each individual weight will be drawn from some distribution, PW. So every little point in the weight matrix will have its own prior. And something simple could be like a normal with 0 mean and some variance. We could also want to add dependence between the weights. That is, we'll define a prior jointly over the whole weight matrix. So now all of these variables are given a prior through one density function. And analogously, we could do that with the multivariate normal. And so just here, I've chosen a 0 mean and some covariance matrix. And note the dimensionality of this covariance matrix is DL minus 1, where this is the rows and DL is the columns. It'll be size DL minus 1 plus DL squared. And note this wouldn't be the number of free parameters, it'd be less than that, but this would be the size of the covariance matrix. And of course, we go further still and try to define a joint prior that models all of the weights at once, and where presumably you could induce dependencies between the first and last weight across all the layers. But as you can imagine, this is not usually done. We'll get into more about priors in a subsequent video, but it's hard to set such a prior, and it's just hard to instantiate it. So again, if you wanted to set a multivariate normal prior over all of the weights, the sigma matrix would be number of total weights squared. And so if you had, hundreds of thousands or millions of weights, this would be an extremely large covariance matrix. and you'd have to do operations with it, like invert it. Okay, so now that we've walked through some simple priors, we can now define the posterior. So we'll say the posterior over W1 to WL, all of the weight matrices at every layer is of course given by the data model we saw before, P of Y given X and all the weights, times our prior. Here I've written the prior per layer. And so we have to, for this product comes over all layers. And at the bottom, we have our marginal likelihood. And recall the marginal likelihood is defined as just this thing in the numerator, but integrated over all the parameters. And so we have our observation model and our weights, and the weights will be integrated over. Note this posterior can have dependencies across all weights, even though we've defined a prior that factorizes across layers. Now that we have the posterior, kind of the most important operation that we can do is from the posterior predictive. And so now we have our observation model, but now we have a new data point X star. And of course, we have our posterior right here. And we integrate the two over the weights, and that gives us our posterior predictive distribution. And that is the quantity I showed before. In particular, for this model, I set a normal prior for each weight individually with 0 mean and sigma squared equals 5. I put a gamma prior on the observation noise. And for the y, we used a normal distribution, again, with the mean determined by a 2 hidden layer neural network with 30 hidden units, and our response noise that was drawn from the gamma. I hope this has gotten you excited to learn more about Bayesian neural networks. And please check out the next video about priors.